Okay, let's get started. So today we are doing an iPad class instead of slides. So I've never actually done this before in a classroom and simultaneously on YouTube, so we'll see how this goes. Marjana will be monitoring the YouTube chat because I can't see it. Okay, so before we start, I think there's only one question from the anonymous form, which was regarding if we will cover efficient transformers. We haven't covered transformers yet, but we will cover efficient transformers as well. That'll be something new that from the last year's class. However, we are still quite a ways away from talking about these more complicated models. Okay. This is starting out well. All right. So, and please, if you can't read what I'm writing due to either size or bad handwriting, which is going to happen, just let me know and I can clear things up. So this class, actually, we're going to be talking about basically all of the important algorithms that we'll be using for the rest of the semester. So this is a very important class, at least conceptually. When you start implementing these models, you'll notice that none of the stuff that you're learning here, you actually have to think about at all. All of the libraries that are built these days handle things like gradient descent and backpropagation, which is the algorithm. These are the two algorithms that we use to actually train the neural language models that we were talking about in the last lecture. So last time, remember, we went through the forward propagation phase where we got from these initial word embeddings all the way up to final distribution over the vocabulary. And I told you that we randomly initialize our model parameters, and then through a process called training, we adjust those parameters to make the predicted distributions become more and more reasonable, fit the training data set. So we're going to do, first, before we cover backpropagation, we're going to talk about the loss function that we use in neural language modeling and generally in all multi-class classification tasks. And I'm going to put this here, the cross-entropy loss. Once we talk about that, we have our first loss function, which tells us, how well our model is doing at this current point in time. We will then talk about how to use this loss function to update our model parameters through backpropagation, and we'll go through. Turning this off. We go through a couple of different examples. So we'll go over just a straightforward. I don't know why I'm writing that down. Feed forward and a recurrent neural network. So this second part will introduce a variant of backpropagation called backpropagation through time. We will do both of these with single neurons. In practice, you'll be using matrices and vectors for everything. You should check out the fall 2020 lecture. I linked it on the course page for backprop through linear layer. And this is with a matrix and a vector. But I figured we would do something different this time. So yeah, you should definitely check out that video to learn how the actual models that you'll be using, which all use matrices and vector-based inputs, work. And I have some composition function that combines all of these things into a single vector and then outputs the prediction of books. So we talked about how this output layer is accomplished through a softmax, right? So maybe it's using some weight matrix, and maybe we have another weight matrix that is, taking the concatenation of these words and then projecting it into some hidden space, right? So maybe this we're going to call H, our hidden representation, and these we called C1, C2, and C3. So just as a refresher, in this kind of model, what are the parameters of the model? What are the things that we want to actually train to make this model yield better predictions? So what specific things? Okay, so we have W1 and W2. These are our weight matrices associated with composition and output, respectively. What do we have other parameters? Right, so the word embedding C1, C2, C3. These are embeddings that are learned as part of the process. So the input to this model is actually the text students open there. This text is then fed into some sort of lookup. So every word type in our vocabulary is associated with an embedding. If I see students, I will go look up the students embedding, which is some dense vector, and the parameters of that will get trained. All right, so let's just write out the equations of our, our concatenation-based neural language model using this notation. Of course, I turned this off again. So this looked something like, here the semicolon represents concatenation. And then we had O, which we'll call our output predicted distribution. That was softmax of W2H, right? So here, if you look at these equations, are H and O parameters of the model? Why are they not parameters of the model? Exactly. So H and O are intermediate variables, right? They are functions of the actual model parameters, but they themselves are not separate entities that are part of every single training example, right? They're dynamically changing as we get different inputs. So, H and O are intermediate variables. And so if we're going to be training this neural language model, we're not going to be updating H and O, right? Because they're actually functions of W's and C's, and these are the parameters that we're actually going to be updating. All right, so that was just a brief review. Now let's proceed to the training process. So what we're interested in is how do we train this model to make better predictions. And we'll follow a series of steps, but the overall algorithm that we're using is called gradient descent. So step one of this process is we need to define a loss function that tells us how bad is the current model at predicting the next word. In our running example here, the word is books. So define loss function. We'll call this L theta, and theta generally represents all of the model parameters. So W1, W2, all the C's get rolled up into this theta, and we're going to use that to describe all of the model's parameters. All parameters. That tells us how bad the model is doing at predicting the next word. So of course, in our application of neural language modeling, the task is predict the next word. For some other task, this could be predict the sentiment label or predict some other properties of the text, but we're talking about language modeling here. So the specific loss function we're going to use is called the cross entropy loss, and it's very intuitive. The definition builds on many of the things we've touched on in the past, and again, this is the loss function that's used for any multi-class classification problem. So just to explain how this works, let's say we have a training example. And so our standard training example, students opened there should go to books. So this, again, is our input prefix, and this is our target word. And we know that our model is going to output a distribution over the entire vocabulary. We want to know how good is this distribution at predicting what is observed in the training data, or in this case, just books. So specifically, why do I keep doing this? P of books given students opened there. And we just want the model to maximize this probability, right? Because if it maximizes this probability, it's minimizing the probability of every other word type in the vocabulary, which is, of course, not correct based on the single training example. So we want to maximize this probability. When we are working with machine learning algorithms, we're generally going to be using a lot of different types of optimizers that require or prefer minimizing a loss function. So, and we also talked about another issue with using raw probabilities, right? We run into these numerical instability issues, and we prefer to use the log. There's also other reasons why we would want to do this, but just the intuition is we want to maximize the probability of the correct word that we observe in our training data given the input prefix. What we actually do in practice, we minimize the negative log prob of books. So this, then our loss function L becomes this. I guess I can some quotes around this to make it clear that that's a contiguous sequence. And so this, in our setting here, this is equivalent to the cross entropy loss. And let's just go through a quick derivation of why we're calling this the cross entropy loss, because some of you might be familiar with the definition of cross entropy as, a distance metric between two distributions. Why is that the same as this thing up here? And it's pretty easy to see. So our model, which is, okay, let me try and use these cool features. This thing. Nice. Oh, no, I got it. All right, whatever. So our model is predicting a distribution over the entire vocabulary, right? So remember in our example we had like books, stamps, lamps, all these other random words in our vocabulary, right? Word types. And maybe the model is assigning some probability to books, but it's actually pretty bad, so it thinks lamps and stamps are higher probability. So let's say this is our model distribution. Meanwhile, we have a training example, right? The data. The data is telling us students opened their books. And then you can view this as a distribution over the entire vocabulary again, right? Books, stamps, lamps. Oh no. Where all of the probability is on books, and there's 0 for every other word type in the vocabulary, right? So P of books given all this stuff, is 1. This is what we observe in the data for this particular prefix. So we have 2 distributions now. One is a one-hot distribution, right? All the mass is on books. The other is this model prediction, which is clearly wrong, right? And so what we want to do is, let's see, get this, right? I don't know why I'm doing this. All right. So the cross entropy loss then, if you have 2 different distributions of 2 disks P and Q. Okay, maybe it'll come in useful now. So let's say P is our data and Q is our model distribution. Wait, yeah, P is the data and Q is the model. So the cross entropy is defined as, wow, that was bad. The sum of over all word types in the vocabulary of probability from the data distribution times the log of Q of the model's prediction here, right? So this comes from the model, this comes from the data, this is the definition of the cross entropy. But we know that from the data that there's only one term that's non-zero, right, over all these word types. So 1 for books, 0 for everything else. And so this just becomes the negative log probability of the model's prediction of books, right? Which is, sorry, let me make that more clear. Books given students. This is the negative log prob of correct word. Okay, so this is the loss function that we will be using for neural language modeling. I mean, there are variants that people have proposed, like maybe you can smooth the data distribution using some sort of data set statistics. Like maybe students open their laptops is equally plausible under some context, and you want the model to know that, in which case this cross entropy loss no longer just simplifies to just one term. But in all of the huge scale models that have come out today, we're just using this simple objective function. All right, so any questions while I turn this pen on for the 50th time? Yes.
Just one question about cross entropy loss, whether it's the dominating loss in the backpropagation.
Yes. Great. All right, let's move on then. How are we doing on time? I guess, all right. Okay, so we have a loss function. Didn't need to write that. And now the real next step is to compute the gradient of this loss function with respect to all of our model parameters. We need to compute gradient of L with respect to theta, the model parameters. And this looks, okay, that's a little, it's just this model params. And we'll be using this notation for the gradient, the derivative of this loss with respect, yeah. Well, so let's say I have a very long book or something that's in my training data, and I have, you know, like 3,000 words before this prefix students open there is observed. Then the next word that I see in this book, in this book is books, right? And so the intuition is that on aggregate, only the word books is going to be a suitable next word in this given context, in aggregate. And so this is what you observe in your training data when you're using maximum likelihood estimation, right? So yeah, so when the prefix gets longer and longer, you get more and more constraints on your data. So this makes the maximum likelihood estimate method quite reasonable. But you could also, introduce some other, like add some sort of smoothing or something like that. Actually, we'll see later on that for machine translation, you often use something called label smoothing, where just like you say, perhaps it's unreasonable to put 100% of your confidence on books, even if the context specifies it down to, okay, this is some book-like thing. It could be novels or textbooks or something like that, right? So one approach called label smoothing, you subtract, say, 10% of the probability from books. So the probability of books is now 90% under your data. Then you just evenly assign the remaining 10% across all of the other word types that weren't actually observed in the data. So this seems to help sometimes. It's still not commonly done for the large-scale language models, but who knows? Maybe in the future people will come up with more intelligent things. But yeah, this is, if you're training with maximum likelihood, you're going to try and maximize the probability of the data, which means books is what you observe, so that's what you want to train on. All right, so we're computing the gradient here. What does a gradient actually mean? The gradient, okay, let's use the yellow highlight. The gradient tells us the direction of steepest ascent of the function that we're taking the gradient of L. Intuitively, it tells us, let me write this down, tells us how the loss changes when we modify the parameters. So this is exactly what we want, right? We want some function that'll tell us if we modify the model parameters in this way, then the loss function will change. It'll either increase or decrease, right? And actually, we want to take a step in the direction that minimizes the loss function, right? So the gradient will give us the direction of steepest ascent, or maximizing the loss function. So when we apply gradient descent, we always take steps in the direction of the negative gradient in order to kind of minimize that. So let's be, hopefully this will make more sense when we look at a simple example, but let's say we compute the gradient. After computing EL E theta here, take a step in direction of negative gradient, thus minimizing. Don't know if I spelled that right. Just going to assume I did. So this looks something like, if I have theta as my model parameters, and I want to take a step, I'm going to change these parameters, right? So theta sub nu is going to represent my new parameters, which I hopefully are doing a better job of predicting the next word. I'm going to compute theta sub nu by taking theta sub old and subtracting, going in the direction of the negative gradient, the step in the direction of the gradient. So this thing is the gradient. This eta is called the learning rate, and it controls the step size. And so those of you who are familiar with machine learning, this is probably a review. But just in case, let's go through a simple 2D example to hopefully make this more clear. So let's say I have a plot, and I have my loss, L of theta, on the y-axis, and I have theta on the x-axis. So let's say theta is just one scalar number, and L of theta is also a number. And let's say my loss is some kind of convex function. This generally is it's never the case with a deep neural network. These loss functions, the loss surfaces are highly non-convex, but we use convex optimization methods to train these models in practice. It seems to work well. There are reasons for this that we won't get into in this class. But if you've been following along in the class, you'll notice that whenever I talk about these parameters, I always mention that they're randomly initialized, right? So this theta, when we start with no training, we have no idea how good it is at predicting the next word. And we're going to start somewhere on this loss curve with our random parameters. So maybe we start up here. And this is going to be our theta sub 0. And we just randomly initialize this. And we got a model that's not great at solving whatever hypothetical task this is. Right? Ideally, we would want to get all the way down to the minimum of this loss function, as that's where the model is doing the best. In our neural language modeling example, right, this L, the loss would be the cross entropy loss, right, the negative log probability of the correct word. And so we want to minimize this function, which is equivalent to maximizing the probability of books given students open there. So how does gradient descent actually work? Well, when we're here and we calculate the loss given our model parameters, we're also going to calculate the gradient. That's going to tell us the direction of steepest ascent, and we're going to take a step in the direction of steepest descent, right, the negative step. So our gradient might look something like this, and when we take a step, we're controlling how far down this curve we go with this eta, right, the learning rate. So if eta is really small, then we might only travel like over here for our next iteration of the parameters. If eta is large, so if we compute it again, maybe we come over here. In general, there are many methods to control the step size. We often use methods that have an adaptive step size. So at different iterations, even for different parameters, the step size is changing. When we talk about transformers, we'll see that the learning rate schedule used for transformers is particularly complicated. But for standard training, you can just assume you start with some fixed learning rate and you just go from there. So eventually, maybe we get all the way down to the bottom, and this is where we would stop. Who knows how we decide when to stop updating our parameters? So that might be true if we have a convex loss function, which we do in this case, but let's imagine that's not generally true in the big networks that we'll be training. What's that?
Is it me or him?
You.
Oh, okay. You can, I guess, put some sort of limit to the change in loss. So after the change in loss becomes very, very small, like 0.01.
You could certainly do that on your training set, but more often people will do what you describe on the validation set, right? This is a held out data set, so you want to know how well your model is generalizing on new data, not just how well is it doing at overfitting this training data set. So exactly what you said, and even what you said, right? When the loss, or if you have some classification task, maybe you're interested in the accuracy or something like that. When that stops changing on the validation set, then you can stop training. So this is the most principled thing to do. When you have enormous data sets, you generally don't do this, even though it would be great if you could. Instead, people training these huge scale models will just pick a number of time steps, a number of gradient step updates, and then they'll just train the model for that number of steps and then say it's done. So there are many reasons for this that we'll cover once we get to transformer type models. But yeah, so let's say in this tiny case, it's easy to know when to stop. And once you stop, now you have theta sub 3, which is doing a much better job of solving whatever this task is. All right, so that's the general intuition. I should also note that this learning rate here, learning rate is a hyperparameter. Although it depends kind of on the learning rate schedule could also be a hyperparameter that controls the learning rate. But in general, a hyperparameter is something you decide on before starting this whole training process. It's not a parameter of the model in the sense that we're not learning this through our process of gradient descent, right? It's something that actually controls how the model is being trained. So other hyperparameters in this kind of setup are, the dimensionality of the word embeddings, right? How many dimensions should they be? The dimensionality of this hidden state H, if you have multiple layers, the number of layers could also be a hyperparameter. As the models get more and more complicated, there are generally more and more hyperparameters. You can see that tuning these hyperparameters, which we also do on a validation set, that can be really difficult if you have a lot of them and different combinations to try. So there are approaches, which we won't talk about here, that are focused on automatically figuring out the best configuration of hyperparameters. In general, I don't think people are using those all that much versus just trying to max out whatever they can train on their GPUs that they have and the resources that they have. Do you have a question? Yeah, that's a good question. Sorry, I should have mentioned this. So I've just shown this I haven't really specified, right? But in practice, we commonly do mini batch training where you compute the gradient over not just one example, which would be just vanilla stochastic gradient descent, but over a batch of examples. And the batch size is another hyperparameter. Maybe I can write that down. Is important hyperparameter. So the batch size controls how many examples you're going to take a gradient estimate from before you actually do a step. And so in these kinds of language modeling problems, it's generally the case that a bigger batch size leads to a better model. When we get to that point, I'll link some papers that show empirically that this is the case. This is also the case, it seems like in general, just like if you're working with these huge models, bigger batch size is always better.
So in that case, it is possible that there are some candidates which students open their books and students open their laptops. What would be the probability distribution and the loss function?
Yeah, so if they're both in the same batch, say, it doesn't even matter, right? If both of those are in the training data, the model will be trained to predict the books with probability 100% whenever that example comes up, and laptops with probability 100% whenever the other thing comes up. If they're exactly the same, the optimal model distribution will be 50% on both of those. Yeah, but in general, like as you add more and more context, you would expect that these duplicates decrease, right? Because how often are you going to have the same exact sequence of 300 or 3,000 tokens that differ only in the next word? Yeah. I mean, okay, sorry, I've forgotten to repeat the questions, but for those larger models, you have to balance a couple of things. One is you may know that if you do hyperparameter tuning, you can get a better performing model. But on the other hand, you also have, you know, the limitations of your own like compute resources and things like that. So if you know in general that a bigger batch size is going to be better, why not just max out your GPU with the biggest possible batch size you can do? And you know, when you're training at that scale, you usually have hundreds of GPUs, or you're using TPUs or something like that. So yeah, I don't know. It might also be just easier to train a good model when it's at that scale. Like those hyperparameter decisions may not matter as much as they do with smaller models. But this is all conjecture. I don't know.
Things like the loss function or something else, like stuff which is not obvious that the batch size should be increased.
Yeah, so I mean, this kind of thing usually comes up in research papers, right? Because it's very expensive to figure out, you know, that, okay, batch size is a crucial hyperparameter. You have to do so many experiments showing that this is my performance with a batch size of X, this is it with 2X, this is it with 4X. And not many people can do those experiments at scale. The other issue is that models behave differently at huge scales versus at small scales. This is something we'll talk about maybe in an entire lecture here, because it's very interesting. Like the models seem to need to be some certain size before they can unlock a lot of interesting functionality. Yeah. Well, I can say in my research group, that's generally the case. We obviously could try with smaller batch sizes as well, but especially with complicated tasks involving large-scale LMs, bigger batch size is usually best, and it's limited by how many examples you can fit on whatever GPU or set of GPUs you have access to at the moment. That might not be true. That's generally not true. For smaller models, you need to tune the batch size, because it could be that a smaller batch size works better. It also is dependent on the data set size, like the number of total training examples you have. I mean, intuitively, if you have a smaller batch size, you're getting more updates in general. If you are talking about a budget of like, I'm going to compute forward and backprop for n total examples, right? If I use a bigger batch size, then maybe my n is, my number of steps is going to be smaller than if I use a much smaller batch size. If I use a batch size of 1, I'm updating after I see every single example. But that may or may not matter. I don't know. This is really unexplored. It's mostly just empirically that people know that these things don't behave the same at different scales. All right, so I'm gonna, okay.
There's one more question. Can we also tune hyperparameters on train set, like just train multiple models?
I mean, you could train multiple language models and see which one gets a lower training complexity, but the downside of that is you might be getting models that achieve a lower loss but are also overfitting the training set, and they actually do worse on the validation data. So that's why it's always important to use the validation set to gauge how well your model is doing. All right, let's, yeah.
I was just going to ask, are we going to cover meta learning?
Yeah, we may or may not. You can put that in the anonymous form. Okay, so let's actually go through okay. That's a good question. So generally, there used to be ways in which, like prior to the last couple of years, where you might reset the learning rate after every X epochs. So an epoch is one pass through the data. And essentially that has the, with certain optimizers, that has the effect of drastically increasing the step size, which allows the model to kind of jump out of any minima it might be stuck in. These days, people don't really do that. I think the optimizers are good enough, coupled with learning rate schedulers, that they don't, in practice, get stuck all that often. There have been some papers that show that there aren't that many local minima in these loss surfaces anyway, so maybe that's a reason, but yeah. Okay, so I'm going to ignore all further questions and start the example, because we haven't even talked about how to compute the gradient yet. We've just been using it as a term. So, okay, I want to use black color. Simple example. Okay, so we've talked about the gradient. The way in which we compute the gradient in neural networks is called backpropagation. So let's draw this simple network. I have my input x. I have a hidden. These are just single neurons. They're numbers, not vectors like we've been seeing. That's just for demonstration. So this is h, and then I have an output o. And so to get from x to h, I'm going to do a multiplication with some weight w. To get from h to o, I'm going to do multiplication with some w2. And so remember, we talked about these nonlinearities as being important in deep neural networks. Otherwise, you just have a model that's able to learn linear relationships between input and output. So let's say our network is defined as tan h, which is a nonlinearity. This is an element-wise nonlinearity. Here we only have one element, so it's kind of relevant. Tan h of w1 times x. And we'll define O as tan h of w2h. So this is our network here. We're just going to assume x is our input, so it's just an input scalar. And we have a target y. Y is going to be what we want this model to predict. So the model currently is producing some number O, and we want O to be as close to this ground truth y as possible. So highly simplified example, right? So what are the parameters of this model? I've already told you x is not a parameter. It's part of the input. So what are the actual parameters of this model? Right, W1 and W2, right? They're the only parameters of this model. And so when I compute the gradient, I will compute two partial derivatives, right? I'll define a loss and compute the partial derivative of the loss with respect to W1 and with W2. Then I'll update W1 and W2, and hopefully we'll do a better job at predicting this. Okay, so let's do the forward prop. I mean, we've already done this. So forward prop. To get O given x, I just follow these two equations, right? So let's say I've done this. Next, let's compute the loss function. So in this case, since I've given you no info on what this task is, because it's just a toy task, let's say it's some sort of regression task. The simplest possible loss function you can use is a square loss. Some of you might have seen this. Here, it's just L equals 1/2 y minus O squared. So y here is a target. Again, this is part of our input data. We're getting these x, y pairs in our training data, and O is the model prediction. So this is a different type of loss than the cross entropy loss that we've seen. This one is just easier to take derivatives of. It's very straightforward. Squared loss. Okay, so we've computed our loss function, and now in step 2, we're going to compute gradients of EL d theta. And so we know that this gradient is formed by these two partial derivatives, EL d w sub 1, EL d w sub 2. In general, I'll use the term gradient to refer to the collection of all of the partial derivatives of the loss with respect to all of the model parameters. Each of these individual things, sometimes I may also call the gradient, and you might see other people call these little sub-parameter derivatives gradients as well. The terminology is really not great, but Yeah, and broadly you can imagine the gradient is a collection of these partial derivatives. Okay, so how exactly do I compute dl dw sub 2? In general, when we're doing backpropagation, we want to start from the end of the network, the output layer, and work our way back to the input. So we're working our way back. And if we look at the model's definition, we see that, so the output here, the loss is computed as a function of O. O itself is a function of W2 and H. H is a function of W1. So we encounter W sub 2 first when we're working our way back. And so this is going to be the first derivative that we compute. The reason for this will be clear once we compute dl dw sub 2, w sub 1. But this one is pretty straightforward, right? So the important thing to note when we're doing backpropagation is we're going to make use of the chain rule of calculus. So we already saw a chain rule of probability. Now we're going to use the chain rule of calculus. So if you're not familiar with this, did I spell that right? I don't know. You should review your calculus, but basically this says that the partial derivative of this function g of f of x with respect to x is just the partial derivative of g with respect to f times the partial derivative of f with respect to x. So this allows us to compute the partial derivative of a function that is itself the composition of different multiple functions, which is clearly the case in this toy example, right? O is a function of h, which is a function of x, and so we need to use the chain rule to kind of unroll all of these partial derivatives. So let's use this to compute dl dw sub 2. It's very straightforward, so let's take a look at where L is computed. We see that there's this, okay, so maybe we can do this to make it even more clear. Let's just rewrite our equations. L equals 1/2 y minus O squared. And we see that O is the first thing here that we see that's model output, right? The model created O as an intermediate variable. So what is O? O is tan H of W2H. And so now we see W sub 2. So in general, to make this even easier to apply the chain rule, we'll treat even this intermediate thing, W sub 2 times H, as an intermediate variable, a new intermediate variable A. We'll just call it A. So A equals W sub 2H. We'll say O equals tan H of A, and then A equals W sub 2H. So now we can decompose this partial derivative dl dw sub 2 into the product of multiple partial derivatives of these sub-functions that we've created. So we have this. Let's start with dl do times do dA times dA dw sub 2. This is an application of the chain rule, right? So one thing you might want to know, this is one reason why people use functions like the tan h, is that their derivative is just a function of the tan h of x itself. So to be clear, if I wanted to differentiate this, the derivative is just you square the tan h of x and then subtract it from 1. So you don't need to derive this or anything. You can just treat it. You can if you want, of course, but we'll just take it as a known. So it's nice because you don't have to recompute anything on this side. We just have to square something that you've already computed and then do a subtraction. So it's very efficient. Okay, so let's actually compute these derivatives just to show what this would look like. So what is this partial derivative? We see the function L up here. What is the partial derivative of L with respect to O? Anyone want to raise their hand? So y minus o would be this inside part. Remember, o is negated inside too, right? So this would be minus y minus o. And now, what about the partial derivative of o with respect to a? 1 minus what exactly? Remember that we don't want to recompute anything here. 1 minus o squared, right? So this is good because we already computed o in the forward propagation phase. So we don't have to recompute it, right? And finally, what about this one, the easiest of them all? Right. And so we're done. We computed the partial derivative of L with respect to W sub 2 using the chain rule. Of course, this is only one of the two parameters in the model. And now the intuition behind backprop will hopefully become more clear. So let's say we wanted to compute this partial derivative of L with respect to W sub 1. Note that W sub 1, we have to add a few more equations. So we have A equals W sub 2H. H itself is, let's say we introduce a new intermediate variable, B equals WX. So H we can say is tan HB, B equals WX. Whoops, I don't know why I did that. So now we have all the equations we need to calculate this partial derivative. And so how do we start this process? What is the first thing that we want to include in this product if we're using a chain rule? Exactly. So this first term is actually the same, right? Remember, we're working our way back from the output. So we start with O. We see O uses this H. O uses this A. We see that A uses this H. We see H uses this B. And B finally uses this W sub 1, right? So we need to trace back this path in our forward propagation. And at every point, we're multiplying a different partial derivative to compute this final thing. So if we look at those arrows, dO, dA, then dA, d, this is where our first difference from the other derivative that we computed, right? We stopped here at dW sub 2 because that was our goal. But here we need to actually differentiate through this, this H, right? Because W sub 1 is actually used to compute H. So this becomes H. Now we're going to differentiate with respect to B, the new intermediate variable, and finally with respect to W sub 1. So the intuition behind backprop is that there is no reason to compute these two things independently of each other. Why is that? Exactly. So look at this term and this term and this term and this term, right? They are shared between these two partial derivatives. So if I compute dl dw sub 2 first, I can just store this product, right? dl do times do dA, and I can cache it. And when I'm computing the partial derivative of something farther down in the network, I can just reuse this. So I have saved on the computation of these two partial derivatives, the intermediate ones. You can see how this is very useful if I have a very, very deep and complicated network. I don't want to be recomputing a lot of things repeatedly. So the intuition behind backprop okay. Backprop equals chain rule plus caching previously computed derivatives. And it should be clear now that why it is that we start from the output layer and then work our way back, right? If we started the other way, well, we would just be computing this essentially along. It would be not ideal. So the caching plus the chain rule. So many people say backprop is just the chain rule, which it kind of is. There's just this caching component to make it more efficient. All right. So finally, we had the final step, update parameters. And in this case, I have just two parameters, right? So I'll say, w sub 2 new equals w sub 2 old minus this eta dl d w sub 2. And this is how I train this simple toy network to match whatever my random inputs and outputs are. All right. Any questions on YouTube? Yeah.
I think we're getting W1 in the numerator. Would that cancel? So if you can't have a derivative of one parameter in terms of the other one, right?
You mean the derivative of w sub 1 with respect to w sub 2? Where do we have that?
I think D8 by D8 will give you W2.
Oh yeah, let's compute it out and see. So dA dH is w sub 2. But this is not a problem. I mean, this is the value of the partial derivative.
Well, that's okay having one derivative of the other.
Yeah, that's going to happen, right? Because this A is a function not only of H, but also of W sub 2. So, yeah. And in that case, you're using obviously the old version of W sub 2. Other questions? Yes. Yes, that is indeed what the current optimizers, all the good optimizers have different step sizes for different parameters. So if you have, like 300,000 parameters, you might have 300,000 different step sizes, one for each parameter.
Do you update the values? You get the old values. Do you update the values after every mini batch or after one run?
Yes, so if you only update the parameters after every epoch, you're doing just full batch gradient descent. You're just doing normal gradient descent. That is the definition of normal gradient descent. You take a whole pass through the data and then you do one update. If you're doing it after every batch, that is what we generally do. That's mini batch gradient descent. If you do it after every example, that's stochastic gradient descent. All right, so we have about 15 minutes. Let's see if we can power through this. So I wanted to do something a little different to kind of transition between the recurrent neural networks that we talked about last time to attention-based networks, which we will talk about next week. So really, we're not going to spend any more time on recurrent neural networks. But there's a reason for this. So I'm going to stick to the single neuron example, but I'll draw a slightly more complicated network that is recurrent in nature. And we'll do backprop through that. So in a recurrent neural network, remember I have this H sub 0, the initial hidden state. And let's say I have H1, H2, and then I get to some O. So it's going to look similar to the previous thing, except here I have at every time step some input. Oh, let me call this C maybe to fit our notation. So let's say I have like this 2-word sequence or something. It could be students opened. And we know that in a recurrent neural network, I have 2 sets of parameters that are associated with the update equation, right? I have this W sub E, which is used to project the embedding into the hidden space, and then W sub H, which is used for the processing the previous hidden state, projecting the previous hidden state. and maybe I have some matrix W sub O for the output here. So let's say we have the same setup, like I have some target Y that I want to predict using, the square loss or whatever. So the loss we'll say is the same. And what exactly are the parameters of this model? One difference from the previous example is that we'll say that the, obviously we have WH, WE, WO, but we also have the C's. So we're gonna treat these as embeddings. In this example, these are just scalars. They're all single numbers, but in practice, the algorithm that we're looking at will work similarly. You just have to use matrix vector stuff instead of easy math. Okay, so we'll define O as WOH sub 2, so that's this transition here. And we know from our recurrent update equation that H sub 2 is, let's say we're using tan H again, doesn't really matter, WEC2 plus WH H1, and then H1 equals tan H WE C1 plus WH H0. I think that's right. And in the same vein as the previous example, let's just say this inside part is going to be called A, intermediate variable, and this one is going to be called B. So we've actually set up this like tiny recurrent neural network here. And what is a difference that you see with these equations versus the other one in the previous example that might make the derivatives a little more complicated? Yes, exactly. So remember, a feature of the recurrent neural network is that we're sharing parameters across different time steps. And what parameters are being shared here? We see W sub E occurs in 2 of these equations. W sub H occurs in 2 of these equations. In the previous example, we were using a different weight matrix, or sorry, weight for each of the different equations. That's no longer the case here. You can imagine that if I have a recurrent neural network processing 1,000 different words in a sequence, I'm going to have these parameters used 1,000 different times. So doing backprop through this it can be a little tricky, and so that's what we're going to focus on for the remaining time here. But let's start with an easy one. So DL dW sub O. This should be pretty straightforward, right? So yeah, anyone have any ideas? How would I decompose this into a product of partial derivatives given these equations? Yep. Yeah, sorry. W sub O. And this just equals, -1 O times H sub 2, right? So this one is straightforward. Another thing we can do is compute the partial derivative with respect to the embeddings here, the C1 and C sub 2. These are also kind of straightforward because there are, so let's do this one, DL d C sub 2. So let's work our way back. We have DL dO times dO dH2. So now we deviate because the C is actually used to compute the H sub 2. Then we can use our intermediate variable A, and then dA dx2. Sorry, C2. And we could compute this out if we want. So this would be times WO times 1 minus H2 squared times W sub E. Right? So we could also do this for dx, dl dc1. dl do times, I should just copy this stuff, but obviously you can see how caching these derivatives is really helpful. So here we just go through the second intermediate variable, and we have dc1 at the end. But what's trickier is dl, dwe, and dl, dwh. They're trickier because of the shared weights. So the algorithm that we use here is, it's just, you can view it as the same thing as backpropagation, except we unroll this network into a feed-forward network. The algorithm is called backpropagation through time. It allows us to compute the gradients by summing the contributions that are made at different time steps. Okay, so let's just do DL, W sub E, just so you get an idea of how this works. So if we go back to our equations, let's just do the second time step here. So we'll work our way back again from the output layer, which is this O. So the first time we see W sub E is when it's projecting this C2 embedding to the hidden space, right? So, and that happens right here. So this is the first occurrence when we're working our way backwards. So let's just compute the derivative up till this point. So again, we're gonna work our way back through all of this stuff. So this is the product that gets us the derivative with respect to that first use of W sub E. And now the idea, and maybe I won't write this out, is that you just add that derivative to the derivative that you get when you go all the way back to the second use of W sub E, right? So here I would have DL, DO, DO, DH sub 2, then I'd go DH sub 2, DA, DA, DH sub 1, then work my way back to this thing finally, right? So the idea behind backpropagation through time is that at every time step that this WE appears, I'm going to add the contribution to the gradient from that occurrence to all the stuff that I've previously accumulated. So I don't just compute this gradient all at once. I compute it as I move my way back, and I'm computing these partial derivatives for all the other parameters that are occurring here, like these C's and so on. So that's the general idea. And so I'll just say other time steps here. And in general, we accumulate these DL, DW sub E's as we step back through time. And we do this accumulation by just summing. So you can read up on the algorithm backpropagation through time and maybe derive it yourself if you're interested in why exactly we're doing this summation. And so this accumulation combined with caching the derivatives, as you can see, I didn't even want to write this out anymore because I'm just like duplicating all this stuff I've written previously. It's very important to cache these things to make things more efficient. So in backpropagation through time, we're doing the caching and we're also doing this accumulation in previous time steps. So the last thing I wanted to conclude with, and then if we have time I can take a few questions, is the problem with recurrent neural networks, which hopefully will be somewhat clear from this explanation. And that's called the vanishing gradient problem. So intuitively, if you look at this summation, right, what happens in the vanishing gradient problem is that the contributions from time steps that are well in the past tend to become smaller and smaller and smaller and eventually go to zero. There's a proof in the optional reading for today that you can check out of why this happens in the matrix vector RNNs. But it's generally the case that you get very little gradient contribution from time steps that are well in the past. So even though theoretically RNNs can handle, you know, this infinitely long sequence, in practice, if the gradient diminishes to close to nothing for those far away time steps, the model is going to have a hard time learning how to leverage information from the distant past to perform this prediction, right? So the vanishing gradient problem is kind of specific to RNNs, occurs in RNNs, recurrent neural networks, when gradient contributions at far away time steps go to zero. And intuitively, you can imagine that this is happening because you're just doing a multiplication with smaller and smaller and smaller numbers. When you're using weight matrices, you should look at the eigenvalues of those matrices. But intuitively, if these products are getting smaller and smaller and smaller, the gradient contributions will go to zero. So you should see the optional reading for a proof. And one of the motivations behind the concept of attention is to get around this issue where the gradient flow in a model that has attention is able to more easily look back at time steps from the past without incurring this vanishing gradient problem. So that's what we'll start with on next week on Monday. Okay, we have a couple questions. Go ahead.
If you solve the vanishing gradient problem by taking weighted sum, so that you can assign more weightage to the values which are there in the past.
Oh, you mean like upweight somehow these?
Instead of vanilla accumulation, you can have separate weights for, you know.
So that is actually very similar to the concept of attention. We'll see that on Monday. Yeah, did you have a question? Oh. Sorry, can you repeat? Can you be quiet for a sec? Yes. I just meant that you need to do this accumulation when you have shared weights at different time steps versus in a normal feed-forward network, you don't have to do this. You compute the derivative of a parameter whenever it appears in the network, but it only appears once. So you no longer need to, you don't need to keep track of like the gradient up till this point and add to it potentially. Yeah. Yes. Yeah, so that is a motivation behind the transformer where all of the time steps can be computed at once during training. Okay, so we'll take all remaining questions offline. See you on Monday.